We're going to switch gears once again. We're done with momentum. Now we're going to take a look at rotational energy. This, in many ways, is going to be revisiting the ideas behind circular motion from several chapters ago. You might recall from circular motion that we drew heavily on an analogy with linear motion. So in circular motion, we had angular displacement, angular velocity, angular acceleration, and we compared those with the linear values of regular displacement, velocity, and acceleration. Now that we have a few more topics under our belt, we have the ideas of force and energy and momentum, we're going to go back to circular motion and extend that analogy to include these additional parallel concepts. Energy, though, is still going to be energy. We just have to come up with the right formulas for it in the situation of a rotating object. A rotating object is interesting in this regard because the center of mass doesn't have to be moving. Now, it is possible for the center of mass to move. Imagine a wheel rolling across the ground. There's rotational motion and the center of mass is moving. But what if the wheel is just spinning in place? The center of mass is not moving. There is still energy associated with motion due to the rotation of the mass of the wheel. We want to be able to calculate the kinetic energy associated with that rotational motion. How are we going to do that? Let's start by taking a look at a small piece of the wheel. Some small piece that is a distance r from the axis of rotation. And it has some small value for the mass m. We can calculate the kinetic energy of that piece because it goes as 1/2 mv squared. It's just that in this case, the v is the tangential velocity, because it's going around in a circle. So 1/2 times the mass of that little piece times the square of the tangential velocity would be the kinetic energy of that little piece. Keep in mind that the tangential velocity is equal to r, the distance from the axis of rotation, times omega, the angular velocity. So conceivably, I could take the tangential velocity in the expression 1/2 m times vt squared and replace it with r omega. And with just a little bit of playing around with the algebra, I get 1/2 times m times r squared times omega squared. Now, why is this relevant? Because if we look at our analogy, recall that in regular kinetic energy, linear or whatever you want to call it, it's 1/2 times m times v squared. And we know that we have an analogy in rotational motion for v. We call that omega. Energy is energy. I don't care if it's linear or rotational. It's still going to be measured in joules. But if I want an expression for kinetic energy for a rotation, and I have an analogy for v in place, there's the omega squared right there. What should I put in place for the mass? What is the rotational analogy for mass? Is it mr squared? Well, not exactly. The problem is that mr squared is only applying to that little piece with that little mass m and that exact distance r from the center of the rotation. If I change the value of r and if I change the value of m, it starts getting more complicated. So we only have the expression for that little piece of mass. What we want is an expression for the entire rotating object. In the analogy, we're looking at something that looks like mr squared for mass. What is mr squared? To understand that, think about how difficult it is. What would prevent you from being able to start spinning a rotating object? What would make it challenging to rotate? Certainly a lot of mass makes it hard to rotate, but also the location of the mass. Masses close to the axis of rotation can be rotated more easily than masses that are distant from the axis of rotation. So R plays a role in how easy or hard it is to push something into some sort of spin. In the entire object, because of all the possible different little values of R, we can't really use any of them. What we would like is an expression in terms of the overall radius of the object. We'll call that overall radius capital R. The shape of the object is going to affect this mass analogy in rotational motion. Now, this mass analogy is called moment of inertia, and it's represented by a capital letter I. I know that I, the moment of inertia, goes as mr squared, but different shapes require slightly different determinations. So what I've written is that moment of inertia goes as little k times mr squared, where little k depends upon the shape of the object. So this is the payoff right here. In angular motion, we have a counterpart to mass, an analogy with mass that we call moment of inertia. And if we make this analogy, then I have an expression for kinetic energy for a rotating object that's equal to 1/2 times the moment of inertia, capital I, times omega squared, where omega is the angular velocity. K depends on the shape of the object. There are ways to calculate it, but they require calculus, and I'm not going to require that of you. We'll be looking at a table of possible values of K, but first I want to ask you this question right here. Two cylinders, they have the same mass, they have the same radius, but one of them is solid all the way through, and the other has a hollow interior. Which one do you think is going to have the greater moment of inertia? The one that is entirely solid all the way through, or the one where all the mass is distributed close to the rim of the object? Think about it. If you have questions, ask at the start of class. I want to show you the effect of different moments of inertia. And so there's a video right here of two objects being rolled down a ramp. So I'm starting at the 1 minute mark because the experimenter shows you the two different objects so you can see that they're basically the same size, but one of them is a solid and the other is a hoop. So let's take a look at this. Okay. So one of them is a hoop, the other is a solid disc. They have the same size otherwise. Let's see what happens when he rolls them down the ramp. He's going to release them at the same time. The question is, which one reaches the bottom first? Now, there was no trick there. If you run this experiment and you run it fairly, the solid disc will reach the bottom first each and every time. Why is that? Because we're getting a conversion of gravitational potential energy into kinetic energy. Both of them, the centers of mass are moving, so there's linear kinetic energy. But the distribution of mass means that the rotational kinetic energies aren't going to be the same. They If they have the same mass, they both lose the same amount of gravitational potential energy. And they both gain the same amount of kinetic energy. But that's total kinetic energy. Linear kinetic energy plus rotational kinetic energy. The higher the proportion that is linear kinetic energy, the faster it's moving, because that represents the motion of the center of mass. The solid disk is going to have a smaller value for the moment of inertia, which means that there's going to be a smaller amount of rotational kinetic energy, which leads to a larger amount of linear kinetic energy, which means that the center of mass moves faster and it reaches the bottom first. We'll revisit this. Now, the different values of K. If it's a point mass, and sometimes that's going to be the case. For instance, the moon orbiting the Earth in a circular path or a nearly circular path, I can treat the moon as approximately like a point mass, and K would be 1. If it's a solid cylinder or a solid disk like we saw in the video with the wooden disk, K is 1/2. But if it is a hollow cylinder or disk like the aluminum hoop, K is 1. A couple of situations with a sphere. If it's a solid ball, then K is 2/5. And if it's a hollow ball, K is 2/3. Finally, there's a rod. Think of like a baton or something, a baton being twirled. If the baton is being twirled about something through its very center, like you would normally stand there and twirl a baton with your fingers, K is 1/3, but R is equal to the entire length of the baton divided by 2. On the other hand, if you are holding it by one end and swinging it around, maybe holding it like a cane and swinging it around, K is still 1/3, but now R would be the entire length of the stick or rod. Here's an example question. What is the rotational kinetic energy of a tire on a car moving at a speed of 20.5 meters per second? Now, let's see what's going on here because we need the mass. We're going to estimate the mass as 10 kilograms, and we are going to treat the tire as a solid disk. By treating it as a solid disk, we are going to use K equals 1/2 in our expression for the moment of inertia. We will furthermore estimate the radius of the tire as 45 centimeters. Now, if this were a test question, I'd have to give you the mass and the radius. M is 10, R is 0.45 meters. We plug it in, and we get that the moment of inertia is 1.0125. Then it has these awkward units. Units of mass times units of distance squared. So kilograms times meters squared. We have the moment of inertia. Now let's find the rotational kinetic energy. We need the angular velocity. Now, if the center of mass is moving at 20.5 meters per second, that means that the tangential velocity out at the radius of the tire is also 20.5 meters per second. So right out at the full radius of the tire, a point is moving at 20.5 meters per second, so we can find the angular velocity, 20.5 for V, 0.45 for R. The angular velocity is 45.56 radians per second. Radians. Yes, don't forget those units. Radians are the standard unit of angle. Now that we have omega, we plug in to find the kinetic energy due to just the rotation of the tire, and we get 1/2 I omega squared, that's 0.5 times 1.0125 times 45.56 squared, and I determined that to be 1,051 joules. Now, because the center of this mass of this tire is moving, it also has linear kinetic energy. And the total kinetic energy is the linear kinetic energy plus the rotational kinetic energy. But you know how to calculate linear kinetic energy, and now we've seen an example of calculating rotational kinetic energy. So energy is energy when it comes to rotation. But the other topics that we've been looking at in linear motion, force and momentum, those have rotational counterparts that are not the same. And I want to start by looking at force. To understand the rotational counterpart to force, I want you to imagine pushing open a door. If you're pushing near the door handle, if you're pushing on the side of the door that is farthest from the hinges, good. That's the smart way to do it. The dumb way to try and open the door is to push on the side of the door where the hinges are. You can push and push and push and push. You can push with all your might, and you might not be able to crack the door open enough to say that it's open. So you can push with a modest force at the far end of the door, and you get this rotational motion in the door, and it opens up easily. You can push with all your might at the other end of the door and basically get no result at all. What's the difference? And the difference is the location of the force with which you push. How hard you push is important, but also the location. The rotational analog to force is called torque. We see the word in the middle of the screen right here between the quotation marks. T-O-R-Q-U-E, torque. Torque is the quantity that gets an object rotating, just as force is the quantity that gets an object moving. Torque depends upon the strength of the force, and it depends upon the location. And our first order guess for the expression for torque is R times F. But that's not complete. If you are dumb as a rock, one way that you would not be able to open up the door is if you're pushing lengthwise down the door. What I'm trying to say is the way you push open a door is you push perpendicularly towards the plane of the door itself. You just push directly out on the door, perpendicular to the door. Suppose you were trying to push parallel to the door, straight towards the hinges. You're not going to get it moving. You're not going to create rotational motion. So the strength of the force matters. The location of the force matters, but so does the angle at which the force is applied. That also matters. Torque, I'll show you the equation, but I want to discuss the sign, SIGN sign of torque. Keep in mind, just like with angles, if the direction is counterclockwise, it's positive. If the direction is clockwise, it's negative. That convention has not changed in this rotational motion. So, what's the best equation for torque? That takes into account the location and the strength of the force and the angle at which the force is applied. And it turns out it is RF sine theta, where theta is the angle between the force and the radius, the value of R. R points in a particular direction. For instance, if you're pushing on a door, R points from the hinges along the length of the door to the location at which you're pushing. If I'm trying to spin a cylinder by pushing on the rim of the cylinder, R starts from the center of the cylinder's rotation, its axis of rotation, and points out to the location where I push. The angle between the direction of F and the direction of R is theta. If you're pushing directly on a door, then theta is 90 degrees, and the sine of 90 is 1. And that's the maximum possible value you can have. So the magnitude of the torque, RF sine theta, but don't forget the sine of torque, SIGN sine of torque, as we discussed. If it is trying to induce clockwise motion, we would say it is negative in direction. And if it's trying to create counterclockwise motion, we would say it is positive. So in the example you see on the screen of the force trying to cause the circle to start rotating, it's giving it a clockwise orientation into its motion, so it is negative. Here's a conceptual question that hopefully helps you understand the role of R and theta in the expression for torque. We have a wrench and we are trying to loosen a nut, and we have several different options. Which of those is going to be the option that is most effective in getting that nut loose? Is it option 1, option 2, option 3, option 4? And what you should do is you should try and rank these options. Which one is the most effective? Which is the next most? Which is the third most? Which is the least effective option? Now, I'll give you a hint. 2 of these options, in principle, give you the same effect. If you have questions, ask at the start of class. Just as an object can experience multiple forces at the same time, a rotating object can experience multiple torques at the same time. The scheme to solve for that sort of situation, you calculate each torque independently, you determine whether it's positive or negative independently, and then you add those numbers together. If the torque is trying to create a clockwise motion, then that torque is intrinsically negative. You have to have a minus sign out in front, and then you just add up all of the numbers to get the net torque. Take a look at this question, which has a couple of torques in action. We're trying to rotate a cylinder. One force has a magnitude of 18 newtons, and it is acting on a location 3.5 centimeters from the axis of rotation at an angle of 75 degrees with respect to the radial line. Now, in that formula, RF sine theta, you can get away with using the value of theta that's between 0 and 90, as long as it's the angle between the force and the radial line. The second force has a magnitude of 8 newtons. It is making an angle of 70 degrees, and it is 5.2 centimeters away from the axis of rotation. What is the magnitude of the net torque? One of the things that's not said is which force is clockwise and which force is counterclockwise. But it does say that these forces are running counter to each other. One of them has to create a positive torque. One of them has to create a negative torque. Which one it is, I don't know, but it doesn't matter because the question is asking for the magnitude of the net torque. I know that I have to subtract one from the other, and then at the end I just take the absolute value. We take the numbers we're given. For the first torque, we have R1 is 0.035 meters, F1 is 18 newtons, and theta 1 is 75 degrees. For the second force, R2 is 0.052 meters, F2 equals 8 newtons, and theta 2 equals 70 degrees. One of them is positive, the other is negative. I don't care which is which. I know that I have to subtract them. So I made the first force in the positive or counterclockwise direction, leaving the second force to be in the clockwise direction. I plug in my numbers, and I get that the net torque is equal to 0.22 newtons times meters in magnitude. And yes, the standard units of torque are newtons times meters. If that seems a little bit familiar, it's because the unit of energy, the joule, is equivalent to newtons times meters. But in the context, if we are talking about rotation and torque, we explicitly refer to the units of torque as newtons times meters. We don't start calling that joules because then it becomes too easy to confuse it with energy. The units of energy are joules, which are equivalent to newtons times meters. What we say, the units are joules. The units of torque, newtons times meters. If we continue drawing on the analogies, Newton's second law in linear motion says acceleration equals net force divided by mass. If our analogies hold up, is it true that angular acceleration equals net torque divided by moment of inertia? In other words, can I just replace all of these linear variables with their rotational analogs? And in this circumstance, the answer is yes, you can. The second equation, alpha equals net torque divided by moment of inertia, yes. That is Newton's second law for rotational motion. Let's take a look at it from a conceptual point of view. We have two wheels, maybe like the wheels of one of those old-fashioned bicycles called penny farthings. Let's say each wheel has a mass of 1 kilogram. And let's, for the sake of ease of calculation, assume that all of the mass of each wheel is in the rim of the tire, that the spokes themselves have virtually no mass to speak of. Because of that, each of them can be considered like a hoop, and we can calculate the moment of inertia as m times r squared, because for the hoop, little k equals 1 in the calculation of moment of inertia. If I apply a force of 1 Newton to the smaller tire, what force must I apply to the larger tire, which has the same mass but twice the radius, in order to achieve the same angular acceleration? Should F2 be 1/4 of a Newton? Should it be half a Newton? Should it be 1 Newton? Should it be 2 Newtons? Or should it be 4 Newtons? Think about it. Finally, I want to go over an example, a numerical example, that builds on the previous one. Remember, from the previous problem, we had that solid cylinder on which the two torques were acting. The cylinder, we're going to say, has a mass of 571 grams and a radius of 12.2 centimeters, and ask what must be the angular acceleration as a result of those two torques. We need to calculate the moment of inertia of a uniform solid cylinder, which means k equals 1/2. The moment of inertia equals 1/2 times mr squared. M is 0.571 kilograms, and r is 0.122 meters. And I plug those in, and I get that the moment of inertia is 0.00425 kilograms times meters squared. The net torque from that previous problem was 0.22 newtons times meters. To find the angular acceleration, I take the net torque and I divide by the moment of inertia. So 0.22 divided by 0.00425, I calculated that to be equal to 51. The angular acceleration is 51 radians per second squared. Think about this. Think about any questions you have. Don't be afraid to ask them at the start of class. Take care. Bye-bye.